Welcome to this decision mathematics tutorial on Kruskal's algorithm. Let me first of all begin by recalling the definition of a tree. And there we can see that a tree is a connected graph with no cycles. For example, if we were to consider this graph, allow me to add some vertices. What we have here is a fully connected graph that has no cycles. So indeed that fits the definition of a graph. This graph though does not. Were I to add that edge there, I now have a cycle, so that does not fit the definition of a tree. However, were I to consider a subgraph like the one I'm highlighting in green, then that is what you would call a spanning tree. The graph itself is not a tree, but if you consider the subgraph that I've highlighted in green, then that is a tree. So we call that a spanning tree. It spans to all of the vertices. Now let's consider the graph here, and I say graph, perhaps the best term is network, because there are weights associated with all of these edges. The question has no context. Perhaps we could say we are laying fibre optic cable between all of these East London suburbs, and we wish to use the least amount of fibre optic cable possible to connect them all together. So we could, for example, lay cable here, 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 down here, to there, and to there. But I'm sure you can see there are perhaps more efficient ways of doing that. But nonetheless, what I have there is a spanning tree, but I don't believe it's a minimum spanning tree. I think that you would be able to beat me and come up with a spanning tree of smaller total weight than I have there. And that is your first task. I'd like you to pause the video and see if you can come up with a minimum spanning tree. Okay, well, hopefully what you should have been attracted to there was perhaps this edge. Clearly you'd want to try and include that because it's only of weight free, which is fantastic. And perhaps you'd have also been attracted to this edge. You'd want to try get that edge as part of your solution, and you should perhaps have a bias towards trying to include these smaller edges first. I can't include the 8 of course there because that is a cycle, but perhaps that 9 will do. And I'm trying to look for the smallest edges that I can include. Perhaps that 12 will do. And I've just got Ilford to connect, so perhaps I'll connect it there with the 14. The strategy there is known as a greedy strategy, which is actually a technical term in problem solving. It's greedy there because we're trying to get those smallest edges, the edges of smallest weight, into our solution. And indeed, this is basically the basis of Kruskal's algorithm. We just need to learn it a bit more formally. Let me turn over to the next page. And let's look at Kruskal's algorithm. Now, step 1, as you can see, is to list the edges in order. Well, okay, well I've done that here. Apologies, let's go back to the page. Now, I should mention just some exam strategy. Step 1, list the edges in order, is sometimes a separate part to the question, and you would perhaps use one of your sorting algorithms, for example quicksort or bubble sort. But if they don't ask you to use a sorting algorithm, often it is okay just to use inspection. But once we have done that, step 2 tells us to choose the edge with minimum weight. So we're going to choose SP of weight 3. And let's just make a note that we've included that in our diagram. It's important to do that so that we can check for cycles. Next, we choose the next edge of minimum weight, so EB. That's of weight 6. Let's indicate that on here. Clearly that's not forming a cycle, so that's absolutely fine. Next, let's look at SF. That doesn't form a cycle, so we can include that, no problem. Okay, this is a greedy strategy, picking off the edges of minimum weight. Next, we can look at choosing PF, but no, we can't because that forms a cycle. So we need to reject that, but as far as showing your workings are concerned, you should still write it in to only cross it out and then just comment that you're rejecting that and give a reason, and the reason is it forms a cycle. So that one got rejected. Next, consider FM of 9, so this one, yes, we can include that one. No cycle is formed. Next, let's look at SE. We can include that one. A cycle is not formed. MI. We can include that one. A cycle is not formed. MB14. Well, I really don't need to, that actually forms a cycle, but a larger point there is that all of the vertices are indeed connected, so we now have our minimum spanning tree and we just comment on that. We don't need to go through and reject all of them. If you try and include any more of these, it will definitely form a cycle because we've already connected to all of the vertices. So if you try and connect to it via a different path, it will indeed form a cycle. But for the purposes of showing our workings, we just need to say that all vertices are connected. We therefore have our minimum spanning tree of weight, and well, it will often ask you for the weight as a separate question, but if we total up the weight here, we have 11 there, 11 add the 9 is 20, add, they've got 20 there as well, so 40, so 52 in total. And really that's all you need to do in terms of showing your workings. The examiner is able to mark that you are implementing the algorithm correctly by the order that you include your edges. Just let me emphasize a few things. This is a key thing to emphasize, that when you reject a edge because it's forming a cycle, you need to actually write that you're rejecting it. So write it in to only then cross it out. Another thing which I should have mentioned perhaps as I was going through, there were two edges up there of weight 8. Now we could have instead chosen PF instead of SF, and that would have produced a different minimum spanning tree, but it would have still of course been of weight 52. Basically, instead of this edge here, it would have included that one. But that's often an exam question. Is your minimum spanning tree unique? And you can see in this case that it's not unique because we could have chosen a slightly different minimum spanning tree there. Yes, and you terminate the algorithm once you are aware that all of the vertices are connected, and you can just do a conclusion to say that. Another thing that's worth bearing in mind is here we had how many vertices? 7 vertices, and we have 1, 2, 3, 4, 5, 6 edges in our minimum spanning tree. And indeed, it will always be the case, if you think about it, that if you have n vertices in your network, you should have n minus 1 edges in your minimum spanning tree. Okay, well, I've got a few examples for you to look at. So if you'd like to take that down, it's quite a big network, but I've actually ordered the edges for you. Pause the video and have a go at that problem yourself, and the solution will be on the next page. Okay, to the solution, that's what you should have got. And there are 2 more problems for you to have a go at. So if you'd like to draw that graph, which looks, the graph looks like K5 there. Okay, I keep saying graph, perhaps you should say network, seeing as there are weights associated with all of the edges. Pause the video and have a go at that question. And here is the solution. Sometimes they ask you to draw your minimum spanning tree, but that's not too difficult to do. Another thing that perhaps I should have mentioned is please don't use a highlighter pen, because the way that modern exams are marked, they're often scanned into systems and highlighter pens do not show up. So please just use a squiggly line as I'm doing there. One more question. This is quite a big network. So you're going to take that down and give that question a go. And the solution is here. So I hope you found that video helpful on Kruskal's algorithm.